Hello, my name is Joshua Cosgrove. I'm going to be discussing an improved multi-way trading algorithm originally discussed in a paper by Randy M. Kaplan titled An Improved Algorithm for Multi-Way Trading for Exchange and Barter. If you would like to really know more about this topic, I would highly recommend reading that paper. I would also like to apologize really quick for the high-pitched whining sound. This is the best microphone I got, and I think that's what's causing it. Sorry. And before we talk about multi-way trading, we've got to talk about regular trading, what it is. It's essentially just a matching problem. Trader A has an iPod, wants a camera. Trader B has a camera, wants an iPod. You match them together, and they trade. Simple. Multi-way trading, on the other hand, is more complicated. According to the paper, multi-way trading is the process of trading one object for another object through a series of trades that eventually results in the original traders obtaining what they desire. Each trade that is part of a multi-way trade is called a step. If we go back to here, this is considered a simple trade. It's a multi-way trade where the number of steps is 1. Of course, not all trades need to be simple. Let's take this one here as an example. In this scenario, we can assume that Trader A is offering an iPod and desires a camera. Trader B offers a camera and desires clothing. This cannot be completed as they do not have what each other wants. However, there is also a Trader C that has clothing and desires shoes, and a Trader D that is offering shoes and desires an iPod. This can be made to work simply by having Trader A trade Trader D for its shoes, then Trader A offers the shoes to Trader C for clothing. Trader A then offers the clothing to Trader B for its camera. And Traders A trade has been consummated and everyone has what they want. This can of course be generalized through the creation of a trading pool. Okay, this has a lot of subscripts and colors, so let me explain. The trading pool consists of tuples, which we call trading pairs. O denotes an object in the trading pool, D denotes an object that the trader desires, and T is the trading pool. So if it has a subscript D, that means it's a desired object in the pool, and if it has a subscript O, that means it is being offered. Therefore, a trading pair tuple consists of a desired object, OD, and an offered object, OO. The trader who wants to make the trade also has a tuple, a desired trade. It is a tuple consisting of DD and DO. Same thing as before, and the trade pool is the same. There does, because it's a trivial case, exist some ODI, OOI in the pool, such that OOI is equal to DD, and O of DI is equal to DO. That's a lot of letters, just to mean that there's a trade that is offering what the original trader wants and desires what the original trader has. That's the trivial case. Of course, most of the time that isn't the case. It's more complicated than that. So in the non-trivial case, the goal is to create a sequence S that looks like this one. Each trade is partially satisfied by the one after it. So the first tuple is partially satisfied by the second tuple because the object offered in the first tuple is the desired object of the second one. At the end of the sequence, so the very last one, the previous trade of that satisfies this final trade, and the offered object of the final trade satisfies the original one. In this sequence, S is what the multi-way trading algorithm creates. So this is the same as that one before. Before we get into the actual multi-way trade algorithm, we should talk about how you would brute force this as a baseline. Essentially, to brute force it, you would create a tree of every single trade. And since we're looking for a worst case here, the worst case would be if you have to go through every single path to find the correct one, or it simply does not exist. So the root would be the trade you want, and then at each level you would have to add n paths, n being the number of trades in the pool. So the root would have n children, and then would have n children, and then that level would have n squared children because each one would have to have a child that is each other trade in the pool, and that's big O of n to the n, look at that equation down there, and that's terrible. So we need to improve on that, which we will with the multi-way trading algorithm. So now we can talk about the actual multi-way trading algorithm. This right here on the screen is exactly how it's written in the paper. So essentially, you create a tree where the root is the object offered by the trader who desires object OD, and then you check every trading pair where the object it is offering is the object node we're currently working on desires. So originally this is the root, and if it desires what the then you check if what it desires is what the root offers, then we're done and we found our sequence, so we're good to go. Then if that isn't the case, you then check if what the current node desires is not the same as the next one. If that's the case, we set it to the new desire and then go back to step 1 and repeat. Essentially, we're doing a breadth first search of all the nodes kind of over and over again until we find a sequence that we're looking for. That might have been a bit confusing, so hopefully I can clear it up by walking you through an example. We will set the root as trader A, who desires a camera and is offering an iPod. So now we search all the possible trades, which in this case are just the traders, because each one only desires and offers one thing, so each one's essentially a tuple in the trading pool. So we're searching for a trade which offers what A desires. In this case, it's B, who is offering a camera. So now we check to see if what B desires is the same thing that the root is offering. It's not, because B desires clothes and A is offering an iPod. Since B is the only one who offered a camera, we go back to step 1, except now we are working from B and searching for someone who is offering clothing, because that's what B desires. C is offering clothing, and we check so now we check again if what C desires is what the root offers. It's not. C wants shoes. The root is offering an iPod. Repeat. We look for any trade that is offering shoes. We found one. D is offering shoes. And now we check to see if D desires what the root is offering. It is. D wants an iPod, and now we have our sequence. A trades with B, trades with C, trades with D, trades back with A. And everything works out. Everyone's happy. So without applying these 3 heuristics to the algorithm, it's actually not better in the worst case than the brute force algorithm. So I'm going to go through each of these 3 heuristics in turn and explain what each of them are. So the first one, heuristic 1, I'll read it. When looking for a trade sequence, find the sequence that is a minimum length. This essentially means build your tree breadth first and stop once you find a solution. In this case, for example, there's at least 2 possible solutions here, but one of them is much shorter than the other and will be found with significantly less steps comparisons. If we build the tree in a depth first way, we'd first find trader D to trade with, and then we do trader C and trader B, and that's a lot of steps. But if we had just done it breadth first instead, we would have found trader D and then trader E. We would have found that completed the trade and been done. So following this heuristic, you generally take fewer steps. The second one is pretty self-explanatory. When looking for trade sequences, do not allow cycles in the sequence. This can cause the algorithm to repeat itself until all possible and appropriate trading pairs in the trading pool are exhausted, as per the paper. So to stop this, the algorithm simply just says you can't repeat the same one, and then that just stops all cycles from happening and stops that from happening. Lastly, heuristic 3. When looking for a trade sequence, only consider trades that fulfill the requirements of the current trading pair. So if you brute force it, right, and we did this whole thing, every single time we'd have to make 7 new branches. But following this heuristic, which is what the algorithm does, is, we'd only create 3 branches instead, drastically reducing the amount of nodes we have to visit. So now that we've applied these heuristics, we can judge the complexity again. We can revisit it. So as before, we set up the root, and then each level after the root, there's now going to be n minus 1 relevant trading pairs instead of n, which, because we have to take out, because we can't do repeats because of heuristic 2. So now each leveler is going to be n minus h with the height possible trading pairs that could potentially be children. So in the worst case, this is still big O of n to the n, but it's better big O of n to the n. It's less bad. So you're counting less nodes. So in practice, this is faster, and I'll get into that more in a second. The brute force algorithm, for n equals 5, you have 1 at the first level, and then n at the second level, and squared at the third, and cubed at the fourth, so on and so forth. So for a tree of size 5, the worst case is going to be n to the fifth. Since for a multi-way algorithm with the heuristics and stuff, we instead have 1 plus n minus 1, 1 plus n minus 1 plus n minus 1 times n minus 2, so on and so forth, because you're subtracting 1 each time. If you solve this out, combine like terms, you get 20 minus 41n plus 30n squared minus 9n cubed plus n to the fourth, which makes in the worst case it's actually n to the fourth. So again, still n to the n, but way better n to the n. And this chart down here kind of shows you how much better that just removing that 1 degree can make it. And also, this is worst case scenario. In practice, you tend to get much smaller numbers due to the heuristics. The paper gets into some, and I'd like to talk about those and then present some of my own ideas. So in the paper, it talks a lot about these trading websites that could potentially come up, like swaptree.com and the like, and that doesn't exist anymore. Neither of any of the websites that it lists actually exist anymore, and I think that's just because, this is just my opinion here, these multi-way trades require such a high degree of trust, where like if any one person, so it's like eBay, but instead of dealing with one person who might not send their stuff, it's if any of these people don't send what they're supposed to, the whole thing gets messed up, and then how do you deal with that? And it just doesn't seem practical, in my opinion, over the internet. I could see this being useful, however, in more localized groups, localized friends organizing ways to trade certain things, in particular with, like, say they have their trading card collections and they don't exactly know what each other have, and this way it can kind of make that work better. I could see it definitely being implemented something like that. This is very similar to something like the kidney exchange. It's slightly different because this is so your root is like the one person, and then you're trying to make it work for them as opposed to making it work for as many people as possible. But this general algorithm could be used for things like that. And then another thing that the paper talks about that I thought was interesting was also introducing money into this as well. So like there's certain ways to do that, like introducing, so just having an option, just being like, I am also willing to include money as part of this trade, or just say I'm willing to, or maybe like you assign the value of certain things, and then you're like, I have this for trade and I want this, but I'm also willing to pay the difference, if that makes sense. I don't know. I thought that would be interesting. That's just kind of things the paper talked about that could be potential uses for this algorithm. So that's everything I have to talk about. Thank you for sticking through this video. I know it's a little amateurish. I think there's that annoying buzzing sound, and I'm sorry I can't do anything about that. Just like to restate that this paper is based off of an improved algorithm this video is based off of the paper, an improved algorithm for multi-way trading for exchange and barter by Randy M. Kaplan. All the images I used in the video are taken straight from that paper as well, as long as also some of, like, when I put the algorithm, I just pasted that straight from the paper. Yeah, thank you so much for watching.